All right, let's do this. Good afternoon, devotions. Well, welcome to our talk about liking fast data analytics with Spark, and welcome back to whoever was looking at the Spark and Cassandra presentation just a few minutes before. I'm Gerard Mas. I'm the data processing team lead in Verdata, a startup within a larger company, and we do IoT analytics. And here is Andy Petrella.
Yeah, my name is Andy Petrella. I'm the owner of NextLab, and we are doing quite big data projects, and mainly with Verdata for the moment.
All right, so today we're going to talk about Spark. We are going to give you insights on what Spark is, but also how Spark is working internally. So when you get your feet wet into your first hacking session with Spark, you know what you're doing, you know what's happening. And hopefully by the end of this presentation, you will have a pretty good idea how you can apply it to your own business, to your own project. So the first part will be like the introduction to Spark, the foundations, how it works. We'll give a hands-on demo if the demo gods are with us. I will be covering that. The second part will be covered by Andy, where we will have a look at the broader ecosystem of Spark and have some zoom in into some examples how Spark can be applied to analyze a huge amount of data. All right, so maybe you can start by...
Yeah, I would like to know who has already played with Spark. Raise your hands. More. Okay, and Scala?
All right.
Oh, a lot more. That's good. So we have the right audience, I guess. Go ahead.
Okay, in Java 8, Lambdas. All right, you will need Lambdas to make the most of Spark, either in Java or in Scala, of course. Scala gives you a lighter, nicer syntax for it. And that was the advertisement for Scala. Okay, let's go into Spark. What is Spark? Spark is a system, is a framework for parallel computation. Why is it fast? Is as opposed to Hadoop, and let's say the previous generation of big data tooling, Spark is exploiting the increasing amount of memory that's available on machines today. Also, memory is getting cheaper by the minute. So we are going to, instead of having those steps of loading data, putting it into the disk, loading data, putting it into the disk, we're going to hold it as long as we can in memory and operate on top of it. You will need CPUs, of course. I said it's a parallel framework, so you'll need a cluster where to put your data on that will be doing the crunching for you. And you will, of course, need disks, because the amount of memory that you have will be only a fraction of the amount of data that you would like to process. As I mentioned, it's a general engine, so it's not really only meant to do data processing, but it's very good fitted to do data processing. It's very fast. The chart we have there is provided by the guys at Databricks, where they have compared Hadoop and Spark almost 100 times faster in this specific, very beneficial for Spark benchmark. But I think the key element, the very nice way of Spark is that it's abstracting you from all the infrastructure, and is giving you a very lean and functional set of APIs that allows you to treat the data as you would treat it on a local node, using Scala transformations, using Java streams. And we will focus a little bit more on that in a minute. The other thing I would like to mention is that there is a very fast-growing ecosystem, and it's also a very successful open source project. So if you really want to get your hands dirty with Spark, you go to GitHub and you can start looking into the code. This is a bit of the timeline, so you see that Spark is really started to peak. I don't know what happened. My laser doesn't get so far. In 2014, you see that the activity in the community really took off. Well, before in 2013, we have been using it since beginning 2013, I believe. It became a top-level project in February. We had the 1.0 release, which promises a lot of stability, although 0.9.1 was really good as well. And we had this in May, and recently in September, we had the 1.1.0 release that included a lot of improvements on the Sparc SQL side. And we are probably on the ticking bomb for the Sparc 1.1.1 release that will be coming in one of these days. And next to that, you can see the evolution of contributors over time. This thing is taking up with a very steep line. Probably we will have above the 200 contributors for the Sparc 1.1.1 release. One of the medals that Sparc has already taken into its own possession is that they are able to manage the open source project really well. So the contributions are really streamed into the code, and let's say the managers of the community are doing an excellent job on having the contributions done where they are needed. But let's get started with some code. And here we have the classical comparison that if you Google Spark, and you will find this at some point, the typical comparison between the Mapreduce Job and Spark. And what we would like to point out here, there are just two things. From all the boilerplates that we are seeing on a classical Mapreduce Job, there are only two elements that we are interested in, that are the core of our business logic. The map function that is over there, that is just taking the lines of text and tokenizing it, getting the words and putting them together. And then the reduce part where we sum this and we get some totals. And then you see all this, this code is actually reduced to one simple line that will be distributed, serialized and distributed over a cluster. Even more importantly, is that we get rid of all this job setup, job configuration, and job management. If you wanted to put two jobs together, we have to do the configurations there. Here, actually, the union or the pipelining of the different functions are giving the way on how this job is going to be executed. So it doesn't need any additional metadata to provide the execution process. What is the big idea behind Spark? And let's say the end unit of computation of Spark is an RDD. It's a resilient distributed data set. And you need to think of it as a collection. It's a collection of elements, of objects, and we are very familiar with objects. We can manipulate them, but they are immutable objects, so you are not allowed actually to manipulate them on site. You only are allowed to transform those objects from one shape into another, from your original data set until the piece of data, the value that you want to extract from it that will help your business. Why is resilient? And we will see that into much detail later on. This organization, let's say the pipelining, will give us hints on what to do when something fails, and we can reconstruct it on the fly. Distributed, obviously, will be all this. The RDD will be put across executors in a cluster, and if a data set is basically just data that is being transformed into objects and operated on. And as I mentioned at the beginning, the secret sauce, that is no secret for anybody, things run faster on memory. So RDDs are held on memory for as long as we can. And now I'm going to give you an insight on how Spark is working behind the scenes. And at the same time, I'm going to introduce you to the specific Spark lingo. So when you go to the Spark documentation, you can already position yourself, this is my job, and this is where things are being executed. On my slide right now, I have an HDFS cluster, so it's my repository, I have some data there. I have a Spark cluster, it's made of 3 machines. Those 3 machines are called executors. Those are, let's call it the workers, where my code will be being executed as the job progresses. And using that simple transformation to count words, the hello world of the big data, The first thing we did was taking this Spark context and loading a text file. The text file is on HDFS. It's already on partitions in HDFS. HDFS is a distributed file system. So what we are doing is we are actually loading a piece of each of that file, and each piece it comes and lands into an executor. That's the first thing. We are constructing actually an RDD. An RDD is a conceptual thing. When you have a value that is an RDD you can think of it as a pointer to a collection that is distributed in your cluster. So don't try to pass an RDD in a closure, for example, because RDD on its own doesn't hold any data. There are the pieces of the RDD that are actually the data are forming the data. So the data is a distributed thing. The RDD is only saying where the data is. And I'm going to introduce you to another concept, is the partitions. So once we have a volume of data and we put it into an executor, the RDD, as I said, is a conceptual collection, and the implementation of this collection, every chunk is called a partition. So the RDD is actually a set of partitions. It's made of partitions. And then we are going to apply operations, and we start seeing how nice these operations are going to pipeline next to each other. So the first thing we do is to split every line into elements. So these kind of words, colors, blocks, whatever. What we have here are elements, and they are split by unit. And so I took out all these separators, I put them all together. Flat map allows me to flatten the array that is returning from here. And that happens in parallel. So every one of those executors will be applying that same operation. And then we have the map. After this split, we are having a map. We are adding a 1 to every one of those elements, creating tuples of the element and a 1. And then we come to a reduce. A reduce is a very particular function, because the reduce will change the structure of the RDD internally. So whereas we saw that we have a partition that started here, loaded from the data, and every step of the process took the same amount of data, and you applied a function over it. You could even filter, so get smaller pieces of data from the same data. So imagine that we have a failure on this executor at some point in time. I just need to reload that piece of data and apply the same chain of execution. When we come to the reduce, this is a little bit of internal implementation, the reduce will do a map side operation, and it will do a shuffle, and then, let's say, the reduce side of that operation. The map side is taking a local, so it's applying that addition function locally. And it's very important that this function that we use here is associative, because then we can do it on every single partition, and then we can do shuffle around having our result. I mentioned at the beginning that we have a lazy API, and if I didn't, I'm saying it now. So nothing of this will happen until we call an action on the RDD. And in this case, collect is an action. We didn't put it here, but collect will bring your results together to the driver, and then you will have your results captured into a collection on somewhere that you can do something with it. But if you don't need that collection on your hands, let's say on your program, you could call one of the operations that you can have on an RDD to save it to a secondary storage. So let's have a review of what you just learned on the Spark lingo. First, we have a job. So the job is a set of transformations applied to a data set that is actually created by the Spark context. The Spark context is our gateway to the world. It allows us to load data from the outside and put data again in some secondary storage. And then we have a cluster. Cluster is just a set of machines. It's the thing you pay for, either locally or on Amazon or on Google. There's somewhere you will have CPUs running that are all together. They all have an installation of a Spark, or you will be using a resource manager. We won't go into that kind of detail today. You have an executor. An executor is just one of those elements. And so just one piece. So the executor is a worker that takes your job and executes the job. That's executor It's a very simple name to remember. Then the RDD. As I mentioned, the RDD is the, let's say, the logical set of elements that are loaded, that are described by the same loading function, and that is spread and separated into partitions into the cluster. The important thing here is when you are writing your job, you only think in terms of RDDs, and Spark is taking all the hurdles from you to distribute that RDD around in the number of partitions that make sense for the size of the cluster that you have. And one additional element that we didn't mention before are stages. And stages is how the job is being split once Spark is able to build up the chaining of functions. So we talk about pipelines. Pipelines is the operation of the transformation after transformation. And a stage is an optimization. There is some piece of code in Spark that's called a DAG, the directly cyclic graph scheduler, the DAG scheduler, and this guy will take your job and will start cutting it in chunks that can be pipelined. And all the operations that are on top are executed one after the other. So there is actually no creation of intermediate collections. There is no overloading of your memory. You will take the initial data, you will do the flat map, the map, and the map side reduce all at once, one after the other, and you will have your result on the partition immediately. And that is a stage. And a stage is very important because it will give you the resilient part. So when you fail a stage on executor, we are talking about the task. So a task is a piece of this transformation, this stage assigned to a specific executor. You lose one executor, bump, so what you need to do is to replay the stage where you were on another node and then recover the data that already transformed into the shape that you need at the end. And right now, you are ready to go into the Spark documentation and really get acquainted with it, because those are the key concepts you need to know in order to understand what is happening when you are writing a job in Spark. We talk about operations. Of course, you need to get the data in and out. The Spark context is, as I mentioned, the gateway to go in and out. And the input data can be whatever, especially it can be distributed. HDFS is a natural fit, so Spark is compatible with the Hadoop world. And anything that can have an HDFS format will be, or a Hadoop input format can be read by Spark. But of course, there are now companies coming up with their own frameworks and their own adapters to plug a little more natively into Spark. I was talking a little while ago about Cassandra and the Cassandra driver for Spark that will allow you to really bypass some of these Hadoop interfaces and really hook into Cassandra, have this data locality for you actually coordinated by the driver. And at the other side, so you will have transformations. Transformations are lazy. You apply a map and you apply a flat map and you apply a filter and you apply a collect of stuff, and nothing will happen. And only when you call an action, and sorry, there are two collects. There is one that filters data and transforms it, and there is another that collects data into the driver. So one collect is a transformation and the other is an action, not to confuse anybody. Basically, you can keep on going onto the transformations. You will build up those pipelines, and then an action will materialize the operation into the cluster, will have everything executed, and you will have some results in your hands. We classified here those transformations for you, so inner manipulations, so they're the simple operations. You know them already from the Scala collections. They are all inspired actually by the Scala collections. You have flat map, filter. Then we have operations that take two or more RDDs, except Cartesian that takes RDD and produces a Cartesian product of it. But you can have two RDDs and union them. You can have an RDD and subtract another from it. You can have the common elements of the RDD, so you can have basically set operations on top of the RDDs with this cross RDD operations. And then we have the structured organizations, and we have a warning there. Those are expensive. And those are expensive because they are oftentimes triggering that shuffle, and the shuffle writes to disk and reads from disk, so it's not all kept nicely in memory. When you do have a shuffle, you have a penalty. And hopefully I can give you some examples of that in demo. And then so you have tuning operations, you have a coalescence repartition is used to change the parallelism, the internal parallelism of Spark. There are more tuning. So when you have some issues with how the tasks are being scheduled, you can use some of them to repartition your data across the cluster. Then you have actions. And actions, some of them are to fetch the data. Once you have an RDD, you need to call one of these actions and you get the data from the RDD materialized. So that is collect brings all the data back into the driver and into the driver code that you wrote. Take first, they all take a small piece of data, sample will take some sample data, very useful for people that are doing some statistical analysis. They just need to take the sample of a very large data set. And then you have those operations that aggregate results. You can count things, you can reduce things, etc. And output operations are to take the RDD and do something with it on a bulk. So, for example, write it back to HDFS, write it to Cassandra. And you can do actually also some custom operations. Those for each partitions are side effecting operations that you can use on your RDD. And I'm going to talk a little bit about RDD lineage. So when we build up that pipeline, we build up actually a lineage, and that lineage will be broken down into operations that then we can pipeline together. And the shuffle RDD here that I put in red will be the one that will reorganize the data into the lineage and put it into different partitions. But the lineage is important to understand because when you start creating a job like we have there, we have the words and we reduce by key, but then we have the scores. We want to have all the words organized by how many times of the word frequency. Yeah, very interesting if you're doing some analysis, some simple analysis on text. Then what you see is that we built one lineage where the words RDD will be here, and the score RDD will just be building up on top of that one. And there is another very important part of Spark is that you can control the way RDDs are being cached. So you could introduce a cache after the shuffle and apply those two operations in a very cheap way, especially if you want to break down. So this is forming a tree. As you see, it forms a natural tree. If you would have some other operations departing from the same place, you typically would like to cache that node where operations start to spread, where the tree starts to spread around, where it makes sense. Of course, it's very dependent of the business logic, but when you see that your lineage is starting up and up in the tree, look for the node where this tree starts and apply a cache there. Most of the time will improve a lot the performance of your job. And one additional word on the support that Spark offers at the moment. So you have a Java API. We have the achievements there, the API achievement for Java, and then we have the shell and the notebook for Scala. Those notebooks are actually third party, one created by Andy here. And the shell, the very interactive shell that comes with the Spark. You have also a Python API and an IPython notebook that is compatible with Spark. That's actually translating into Spark commands behind the scenes to give data scientists that interactivity that is necessary when you are doing data exploration. And finally, we have R. The R project is evolving. Maybe you can talk about it afterwards a little bit. But it's evolving right now. This is not very stable yet. And okay, now let's have a little demo, little hands-on demo, and hope that things go well. And here I have maybe I'll just start it up. So when you
take this otherwise.
The first thing you will see when you come to Sparc job is when the Spark it comes with this shell, and here I'm starting the shell with a local node. So I'm running. Yep. I'm not sure you can do that.
No.
No.
Oh, shit.
Well, it's a good screen. All right. So here we have our context. The context is the Spark gateway to the world, and what we can do is to ask Spark. I usually do this because I have a bad memory and I want to see what my files are. So I have few files locally. What I'm going to show is just the application of that transformation that we did on the screen, and how can you apply this hands-on on a small local cluster. So now we're running on one machine. There is no clustering. And what I'm going to do, I'm going to load, and I have a cheating sheet somewhere here, because I get nervous when I'm in this. And then Grimm does a book for kids, the Brothers Grimm. They wrote Red Riding Hood, Hansel and Gretel, and many other stories. And what we're going to do today is we're going to analyze it. We're going to see what is inside without having to read it all. All the stories are there, packed together. And the first thing I can do is I can see the amount of lines that my book has. We have 9,000 lines. And now I can split that thing into words, and we can say the RDD.flap map, and then every line we're going to split it into a line split, and we take all non-words as delimiters. Yeah? Oh, I have my flat map already. Nothing happened. I didn't apply that operation to the 9,000 lines that I have there. Something. If you really want to see what happens when you apply an operation, as I mentioned, you need to do an action. So, for example, we can do say words.count, and then this will start applying that flat map and get the amount of words that we have available there. And we can also do words and take few of them, and we explore there. So the book is coming from a project about open ebooks. It's called Project Gutenberg, and they make these books available for free on the internet. They are also open, so people can download them legally and have some lectures. But this doesn't tell us too much. So we have an ebook from the Grimm's brother about fairy tales. We are going to start now to process that data. So we are going to say word count is words, and I'm going to apply the same thing. So first thing is I'm going to apply a map of the word into word 1, and I'm going directly to reduce by key, and I'm going to sum those. Okay, boom, voila, nothing happened again. I need to ask for it, and this time what I want to show you is that lineage. The bug string is your friend, and the bug string says here we are departing from that Hadoop RDD that is based on the Grimm.txt file, so it has a link to the source. And given that our source is not changing, the whole RDD can be recomputed to the same result every time. And then on top of that, we are applying the flat map and the map, and then we have a shuffle. And please check every time you're building your jobs, check your lineage with this function, and really visualize what is going on with your data to understand the performance properties of it. It's very important when you are going to scale this up into a cluster to understand how that's happening. And so we have the word count already, and I'm going to take 10. And what we will see we have an array there, someone, bomb, nobleman, shot, grappling, boom, boom, boom. It doesn't tell me anything. Yeah? And luckily, we don't have many of those nasty words, that come very often in every language, actually, but here we will have some like the and is and all that. So if we start trying to analyze these, they are going to become noise for us. We want to take them away. So what we're going to do is we're going to take another stop words. Stop words English, I hope. Bam. And let me see if stop words. Boom. It works. No, it doesn't work. So yes. I will apply my trick again. And English stop words. Boom. Oh, yeah, lowercase. Okay.
Control Shift.
Yeah. Boom. There we are. Okay, so stop words is a list of the words that we have in English that are very commonly used to join sentences together. And so they are the glue between words. And what we can do is then we can say cleaned is this word that we had before, and then we take out the stop words. Come on. This S is okay. So now we have the cleaned, and here I actually made a small mistake. So when we do this, stop words are all in small caps, and we need to actually map every word into a word at lowercase. Yeah. Case. Now we're almost done here. And okay, so we mapped everything to lowercase and we subtract the words. And come on. Again, this S. And okay, voila. There we are. We now have this cleaned. We apply the same operation. So we're going to map this word into a pair. And we're going to reduce by key sum, and we're going to do something additional to this. We're going to map, and we're going to swap them. And I'm going to call this, I cannot do like this. I'm going to call this the scores. And now I can see scores.top 20. And that will give me then a better view of what these books are about. You have man and king and good and time, and day and father home told, mother cried, wife great, and the long door put fell asked. Yeah, so we get a little bit of a feeling of this fairy tale of the Brother Grimm. But at this point, we only saw what the Spark is doing on a local node. This is for you to start learning. And what we're going to do now is we're going to do this for real. So instead of downloading only one, we downloaded 4,000 of those books. And instead of local, I'm going to use my cluster for real, which is it's not very large, it's a small cluster. We have 120 gigabytes of memory, from which we're using 80 at the moment. I'm going to cheat because otherwise we're not going to get out of here on time. So I have my big cluster script over there, and you will see that it's slightly different than the one above. Why? When we were talking about this book and these top words, the size of the two RDDs were pretty similar. So you have a long list of those top words, and you have a book with 9,000 lines. That's not much, but when we are talking about a few millions of lines, then the stories are very different, and we approached here by mapping partitions. Okay, so I'm loading here number of files. And in the meantime, while we're crunching this, I'm going to show you what's happening. So this is a Spark UI. F5. Yeah. And the first thing what's happening there, we are doing the first collect. And I think we are connected to the wrong one, no? Spark Shell application UI.
Maybe go.
No? This doesn't look like it's the right one.
We need to get out of here. Maybe there is another one.
No.
No, nothing.
No, it should be 40.
No.
It's certainly not.
It's weird. Try to.
Yeah. Well, let's go back here.
Go there. See if it's connected.
Yeah.
No, nothing is running on 41. That's weird.
Okay. Then maybe we just skip that demo. Yeah. So normally this thing will calculate everything, crunch about 1 gigabyte in text. It becomes 10 gigabytes of memory, in memory, and it does the whole analysis of the same thing we did, but for a whole body of text. And here it's running, but we just cannot reach the UI for some reason. Let's see here if we have it, otherwise we leave it. Oh no, there we are. There we are. So we are mapping 3,886 partitions. And this thing does not load on the fly, but you see how it evolves. At the same time, I can show you a resource manager, Mesos, and Mesos will be displaying the tasks that are active. So I have 4 tasks, each one executor on each node of the cluster. And I'm using, as I mentioned, 80 gigabytes of memory to do this simple crunching right now. And we also had some demos that we were skipping today. Okay, so this UI gives you information not only about how your task is performing, but also about the RDDs if they are cached. I'm not caching the RDDs right now. This is something we could show in another moment. So running out of time. It also gives you the configuration, very important to inspect your cluster when you're up and running, because when things go wrong, most of the time is because the configuration is wrong somewhere. So that will give you already some insight if you get this far. And we have there the executors that are working for my job at this point. So this Spark UI starts up together with the job. It will disappear when the job ends. We are currently working on the Spark shell, so the Spark UI will live as long as the Spark shell lives. And I don't think we're going to wait for the results of this. It takes about 5 minutes to crunch all the data. And it actually gives us the result. And maybe at the end we can go back and we can see what is the result of that. Just one additional word about it before I give the token to Andy. The Ngram. So what we did right now might seem simple. Google has been doing it for a body of 4 million books to have a view on the change of the culture over time. So we have here a view of the 1800s until the 2000, the difference between good and evil. And to leave you with this thought is very close to immutable and mutable. So mutable is very evil. And now I will give the token to Andy, who will talk about the Sparc ecosystem.
Yeah, thanks, Gerard. Okay, so for now, we just covered the Spark core, right? So we didn't get too far away from the core. What I mean by core is just like an SDK. It's a very low level that Spark is providing. But thanks to its great community, as we saw at the very beginning, these graphs showing how many committers, we have more and more extra layers on top of Spark. I'm going to tell some words about some of them, but I'm going to tell about as well the ecosystem, mainly tooling, and what we can do with that. So the very first thing is high-level primitives. So what I like to say is that it provides new APIs, and it's mainly the rise of the Popolo. So everybody is starting new layers here and there on Cassandra, or I don't know, on DNA, on neural networks or whatever. So I like to say that Spark Core is mainly the fold. I don't know if some of those are using a lot of functional programming, but fold is like the very basic function that function programming can provide. On top of that, you can define like everything. But now we are going to talk about map, filter, and flat map, and so on. The first one, I'd say the most popular one, is the Spark streaming. What does it do? We know now that an RDD is like a distributed collection, right? But it's static. Okay, it's a big, huge amount of data, but it's static. If you enter the dynamic world like we do, like with Cassandra, we end up with some weird things. So for that, we have to go to the Spark streaming. And what does it do? It takes several streams, several big, fast streams, and allows you to see them, all of them, as a single one. That's more or less it, right? So you have plenty of all those streams coming from Kafka, for instance, this particular case, and these streams are seen as a single stream. So this stream has a abstract type, T. So all those streams must share the same type, which can be any. And each of the RDDs that you see there are just the chunks. So what does it do? It takes the stream and chunk every X seconds, let's say. And X is up to you to set. So what we have finally is a part of the streams to be chunked into an RDD, so we can use all the map, filter, and so on that we are providing via the Spark Core. However, this stream is providing this abstraction. So we can directly use map, filter, and so on, group by even, on the D stream directly. This is one of the power of it. So what we can do with this stream and this thing that doesn't work, okay. So what could we do is just define, let's say, a tweet data that packages the data that are coming from tweets, and we can define a D stream. D streams, we can use the very helpful Twitter utils to create streams that is built on top of the streaming context. And on this stream, these chunks, we can use map, take the status, map to our type, right? And after, we can do what? Window. Window is like, okay, we have these chunks, but we have to handle them per second in order to have the final granularity, but we want to have aggregation onto, let's say, window of 1 minute. Window will help on that, right? So it will combine all the RDDs, keep some states, and apply the function on the aggregated RDDs. And then you can simply save to file, and it will save each RDD and partitions to, let's say, Cassandra or HDFS. This is very simple. It looks like RDD, but it's actually very dynamic, and it has a bunch of RDD behind the scene. Why this? Okay. The second one, Gerard has told some words about it, is Spark SQL. You know, SQL, we loved SQL 10 years ago, then we end up with NoSQL, and now, we're starting again with SQL, but finally we'll get back to NoSQL. Okay, I'm going to explain myself. So, we like to manipulate data. So we use relational database at some point in time, and to manipulate the data, that means for querying them at that time, not really for processing them, to query them, they end up with SQL. But with the different new use cases that we end up with, we started to think, okay, now we need some documents, we need some graphs, we need some different structures and different languages to tagger them. Even though the JDBC connector has been built and created for all of those, the inner representation are quite different. But now we are talking about processing, not really querying, okay? So Spark is not something that you expect to query online, right? Even if this stream can let you think about it, it's not really that. So SQL is very important because it provides a mathematical background to query and to process things, process data. This is pure, actually, SQL, right? It might be crappy, but actually the fundamentals are very pure. And they are that pure that you can take them and optimize them, get the plan, right? Without having to do some reflection on the code, etc., like we could do with Kubernetes, for instance. Okay, so, but since analyzing text directly is quite hard, they created another API into Catalyst that is automatically applying the plans and optimization on the fly. Okay, so this is from SQL, NoSQL to SQL, NoSQL. And the last one is NoSQL at all. Okay, so some code, right? What we can do, okay, we apply a SQL, select star from source, and I name it A. Okay, so we can register tables in the Spark context, and they will be seen as tables. RDD, sorry, we register RDD, sorry, to the Spark context, and they will be seen as tables. So we can query that, do like this. But it can be terabytes of data, right? It will be distributed. Then we can use the NoSQL language that I talked about. That is, I take the first SQL and I apply a new where. I call on it a where to specify that I want to have the key. It's a symbol, sorry. So it recognizes a symbol and I say, okay, it's a symbol key, so it will be the name key of the column name key. And I'm going to collect all the data for only this key. Nice. But as I said, SQL is very good for optimization, okay, where applying map, filter, etc. is really hard to interpret. So thanks to that, they can build a plan directly. So you can have access to this plan with the query execution analyzed. But the really fancy thing is that you can also take this thing and adapt it at your will. So it's like, okay, going deeper and deeper and deeper. It's like macro, if you like. So you manipulate the structures. Fine. That was about SQL. So we can now use streams. We can now use data like SQL, like database, tables. Sorry. But now, what could we do with this data? Okay. Mainly, we want to do some mathematics with them. We want to provide some stats, do some predictions, do some classification or whatever. And actually, this MLlib library is there for that. And okay, what I say is that the library to teach them all. Why? Because the usual ones, SciPy, scikit-learn, R, MATLAB, and so on, they are just teaching one single machine, right? This guy, MLlib, is distributing the work, the statistics, and so on in order to teach each machine what are the data. And then we can collapse to have a single view over the data. So what could we do with this? Whoa. Yeah. So we can simply call the algorithms and pass some RDDs to it. So ALS is for recommendations, alternating least square. And what you say, okay, you create the object, you set all the parameters, the tuning parameters you want to apply or to tune, and then you run the algorithm. Let's say you train the model using a training set. And actually, the training set is nothing more than that, than a RDD of data. And this is where sample is very handy on the RDD, because a sample can let you do some cross-validation over the data, because sample can sample the data, but it can also bootstrap the data. That is sampling the data by replacing some elements that has been picked already. Okay, so this is just a quick view over the different algorithms that are available in MLlib. It's lacking of many because it's pretty new, and some are quite clunky, but actually they are evolving fast. That's why Spark is very good, because the community is there to push and to do great things. 8 misses 3, by the way. Okay, GraphX. This is my favorite because I'm a graph nerd. Actually, yeah, graph is there to connect the dots, right? For now, we just see RDD like a stream, a collection of data. But graphs are quite different. When you want to apply processes on graphs, it's a totally different story than with tables. Why? Why? Because one single node it might be connected to a few nodes, right? And in a table, what you have to do is it's a crappy Cartesian with left joins or whatever, but it's quite hard. It will take some time to process them, right? So that's why in Spark, they end up with a different library for that. And the core concept of GraphX is Pregal, right? Pregal is one of these papers coming from the Google Word. And what it does is just sending messages from one node to the neighbor by sending some data, which is part of the computation that they want to apply in a broader view in the whole graph. This is what it does. So you take some edges, drop some nodes, and then you compute things by sending messages between the two. Okay, so can you go? Yeah, thanks. So what you can do, you can ask for a graph loader to load some Twitter followers, just a graph of edges, who follows who. And then you can ask for a connected components. Connected components is like the naive and the quickest community detection that we can do on graphs. It just takes all the nodes that are linked together and separate them if there is no other links all the way in the boundaries. So you can take the vertices, and then you can also join with the user's data in order to see who is where. Pretty easy. Adam. This is my last favorite. Adam is like the new kid on the block in the Spark environment. What is Adam? And I'm going to talk about Thunder, which is for neurals. But it's the game-changing library stack in the genomics world, right? Genomics is like one of the crappiest words I have seen, because it's very old. They're doing very good things, but they are doing things with 70s things, right? So you have your sequencing machine that takes your blood and generates data at a very high speed because everything is parallelized, and then you end up with a text file, okay, quasi non-structured, and then you have to apply your statistics and your model on a single machine, which makes no sense because one single sequence is over 60 gigabytes of data. So they have to take some samples to do that. So this is what you can do with Adam. Actually, what they defined is just a model on the genomics data, which is quite good because you have Avro in the mix, it's very fast, and you have Parquet on HDFS, so you can create the data in a very efficient manner. And how you do that? You can convert your original data file that comes from the machine, you convert it to Adam, which is the Parquet file, you load it, and you have your genotypes. Okay, so tooling. So we've seen now the different libraries that are built on top of Spark Core, I'd say. Now, IDs, or no IDs, I'd say. Because actually when you're doing some Spark, generally what you end up with is some analytics on your data because you don't know what data you have in hands. So you have to do something very iterative, very quick, very sometimes dirty. And having an ID where you can type your Java Scala code is not helping because you have to package, sending to the cluster, execute it, and so on. REPL is not good enough as well because you cannot replay everything quite easily. That's why in the Python world they created what they say the notebook, which is something that you can share quite easily online and has some fancy features to make annotations and so on. So this is what we are going to talk about now. Quick, because I have only 8 minutes left. So the very first one is Spark. It's just a portage. It's just a back end of IPython, but written in Scala to target written in Python to target Spark using the Python API. Zeppelin is a Java fork of Kibana. It has a very good set of features, and I'd say that it's one of mostly, I'd say it's the best in the area for now in the open source world. And the last open source one is the Spark Notebook, which is a Scala-based one. Actually, it's the fork of the Scala notebook itself, and it has a quite the same set of features that Zeppelin is providing. I'm going to be quick on those because we are running out of time. Okay, Databricks Cloud is the non-open source one, and it's built by the Databricks company, which is, I'd say, behind Spark itself. has been created by Maite, which is the creator of Spark. And I'm not going to say more about it because there is plenty of documents. It's very good. You can create dashboards or whatever you would like to do. It's there, almost there. The only thing that is not there yet is the registration, which is not happening so fast. Okay, some examples now. So we've seen the libraries, we've seen some tooling. So what we can do now with these frameworks. The very first thing is mining DNA. So as I shown you, there is Adam that can process a bunch of genomics data. So what we've done is taking the 1000 genome, which is a international project, picking a lot of genomics data and anonymizing them. So you end up with 200 terabytes of data. And what you can do is, okay, we thought with a friend, okay, what could we do with this? Maybe we have, okay, the link between the genotypes and a population. Maybe we could try to classify them, okay? And what we've done, using 40 lines, I just put 5 of them there, or maybe 10. With 40 lines of code, we end up with all the data loaded in our HDFS cluster, Spark cluster, apply some predictions, which was a k-means, by the way, and we end up with some fancy tables like these that was predicting more or less the different populations quite easily. The other one is Geo Data. It's one of my favorite data as well, since I have a very long background in geomatics. Geo Data is particular because they are mostly graphs, right? A road network is a network is a graph. So it's quite hard to do some data analytics on graphs, so it's hard to do some data analytics on geodata. So that's why we took the option to use GraphX to analyze those data. So what we've done, we took the whole OpenStreetMap coming from the USA OpenStreetMap data, the whole thing, and we put it into GraphX, took several minutes, then we asked for the page rank. Everybody knows more or less what is a page rank, just attributing ranks to nodes that are highly connected or connected in a very good fashion. And with this kind of information, it was just a toy. Yeah? We just play with the data. It's not really scientifically, accurate, but still. So what we've done is we apply some statistics that is computing the difference between two distributions, and we end up with scores saying, okay, Dallas is very different from Seattle. 19 is actually very high because the closest to 0 the similar distributions are. And why we have such high divergences because the Seattle is very grid-oriented, the other one is a complete mess. Mining text. I'm going to be very quick on that. It's the last one. Something that we played with Gerhard lastly. We took the whole Wikipedia dump. You know that Wikipedia is dumping all its data every now and then, and it's random. Yep. So it dumps everything into XML, which are multi-line, which is very crappy in distributed environment because your lines are completely spread around the cluster. Anyway, so what we've done is just take the XML, convert the XML in CSV, push it to S3, sampling the data because MLlib has some problem with high number of features. I'm not going to do details for that. And this was done. Can you go? Just one slide before, yes, thanks. So it's very easy. So you take the XML files, you pick the data that you want, and then you save it to S3 using a few bunch of lines. Everything was done in the Spark notebook, actually, so I didn't have to set up any environment. I just have to download it. So next one. So what I've done with this data afterwards, I computed some TF-IDF, which stands for term frequency inverse document frequency. So it computes the import of a term in the document across all documents. And thanks to these statistics, I can use a naive Bayes classifier, which is taking the probabilities and the likelihood in order to predict which document is the most related to a text. So what I've done afterwards, using these lines, I was able to pass to the model that you see at the end. Next, yes, thanks. And I passed some fake data, fake text, that I made myself. And with Java, programming, Scala, blah, 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 the numbers that you see just after are the number of occurrences in the text that I imagine, right? With 50 big names, I end up with the, will these things work? No, of course. With the long double Wikipedia article, so talking about primitives, big numbers, etc., etc. Just lowering the big names and increasing Python, okay, I end up to the code audit, because big names has a less important weight, so it's not really about weight of a data primitive, but it's more about performances, precision, big names, and since Python and leverage is more about code than just structures. Okay, so we had a bunch of data for that. So I'm just quickly show a 20 cluster of 8 cores and 15 gigabytes of RAM. So was quite exciting to use, and this is how we process them. So we have there, going back, yeah. So we have this amount of inputs. You see 1 gigabyte, 2 seconds for processing. We're taking the data out. So it's very fast. Doing on the local machine, just screwed it up. Okay.
So let's wrap up.
Yeah, let's wrap up because it's done. On time.
Here you have resources. If you want to learn more, just download Spark and get running with the Spark shell. All right. Are there any questions? We are run out of time, so maybe if you can come to us with questions afterwards, that will be better. And we'd like to thank you very much for attending the session.